You have it already? Right. Yeah. So I just want to say that the new exercise sheet is out already, so if you still need a copy, you can take one. You have it all? Otherwise I give it? No? Good. Yeah. Take a few. We leave it here in the corner. And maybe as a starter, I would like to explain already one of the questions of this exercise sheet, because we want to dig quite deep, quite quickly into optimal control with differential equation models, which is the combination of the two fields, right? Optimization with a differential equation model. And so we invented a new question specifically for you. And so you're the testers of this question after Andrea. And we thought that why don't we just ask the simple question of you throw, or someone wants to throw two balls, one ball from the left side and the other ball from the right side. And you have a limited time fixed in advance. And the aim is to throw them so that at the end of this time horizon, the two balls are as close as possible to each other in the air or at the ground or wherever they will be at that time. Of course, this could be quite simple if it would just be ballistic flight, right? But to make it a bit more interesting, we have a bit of side wind in this model, so that the balls will be subject to aerodynamic drag, which is a nonlinear effect. It's the same thing that slows down your bike or your car aerodynamically, and this effect will always be against the direction of the real wind. And so the model equations are slightly different, but they are not the subject of this explanation. I just wanted to say that question 2 will have, as an image, so to say, it will have one ball flying like this, and it has this initial condition and this end. The other ball is a bit distance from here, and it will fly like that, whatever. The dynamics, both have the same dynamics, but the wind will be probably from this side, as far as I remember, yes. And there's a maximum speed constraint that you can impose on this angle here. So you can choose any speed that's within this area. The position is fixed, and the maximum speed is here on the boundary, of course. So any of these is possible to choose. One two-dimensional sphere here to choose from, one two-dimensional sphere to choose here. Then it's going through your simulation routine. Of course, we use a Runge-Kutta of fourth order for that. And at the end, you will get a position which we call P1 of t and another position P2 of t. And these positions, of course, depend in a very indirect way on these initial speeds. Yeah? But beautifully, Casadi will take care of the derivatives for you, because it will be very tedious if you would want to compute the derivative of this state with respect to this initial speed by analytic means. It's extremely tedious, very long expressions, but with Casadi that will work out quite easily. And then the aim of the optimization is just to minimize the squared distance of this vector here. Squared because then it's a quadratic and nice differentiable function, but of course it's equivalent to minimizing the distance. So that will be a problem that we will first formulate in Casadi. And we have two bonus questions, and the last one is actually to write your own optimization solver for that problem already. Okay, so Andrea will surely say a few more words about that. Did I forget some important information on the question too?
Not least about the formulation.
No, yeah, okay, good. So it's the first example of a so to say an optimization on the one hand, and it's on the other hand it's numerical simulation in order to define these output functions, and the objective is of course then just to minimize. Here is V1 and this is V2 over V1 and V2, if you the initial conditions of that, to minimize the distance of the two functions. Where I have this index t to indicate that it's the end of the time horizon of interest. Of course, these functions implicitly are functions of the V1 and of the V2. but I don't have that explicit in this notation, but of course that's what you should have in mind when you formulate it as an optimization problem. Okay. Is the rough idea of the optimization problem clear? Because we didn't have that plot in our sheet, but at least we wanted you to have a simple idea. It's something you can invent in a minute, probably, right? Throw two balls, should be close to each other. And then to solve it takes a bit longer, but with the tools that you have learned already until now, including Casadi, it should be relatively easy to do it. And we will, step for step, learn how to solve much more complicated problems, of course. Okay? Yes, if there is nothing more on this question and answer sheet, I would like to start the lecture. And you remember we are talking about Newton's method at the moment, so we are in chapter 2. And I already mentioned to you, and most of you had already a notion of these notions of quadratic convergence, linear convergence, superlinear convergence. So you're all familiar with these notions now. And we continue in section chapter 2, section 2. And we continue with the local contraction theorem. That is something I wanted to share with you for the very general case that we treat here, namely just a Newton type method. So let me just recall what we do before we do anything specific. So there is a theorem, and we will actually just have this theorem. It's theorem 2.4. And I will not state it in exactly the same words, but I will actually explain what we want. We want to search Z star, which is element in Rn, with R of Z star equals 0. That's what we look for, right? With a Newton type method, Newton type iteration. And what type of, you remember what was a Newton type iteration? It was one where we don't use the exact Jacobian, but an approximation of the Jacobian. And our overall iteration would then look like zk plus 1. The next iterate is given by the old iterate minus a correction term that's depending on this approximate Jacobian times the size of the residual evaluated at the last iteration. And very often this mk could be actually the exact Jacobian of R, but usually it's not necessarily exactly the same. That makes it a Newton type method. And we start this at Z0, element in Rn. So that's what we have as a general assumption. And then we I already state what I want to prove or what I want to state. And what we really want to show is that the following holds, that the sequence that we generate, Zk plus 1, the next step that we generate, will be in some sense closer. And so then this will be closer to the previous than the previous distance that we have here. So that's the distance that we had. This is the new distance, and it will be closer by a factor that we call, and this factor I should call kappa k. So this is a bit funny. We have a kappa and a k. Yeah? So that's a kappa, that's an index k. Sorry for the nasty notation. And omega half, and here we have zk minus z star. It's the same expression that we have here. So it's a distance from the optimal solution. And now I should say that this holds, of course, only under some conditions. We even didn't specify kappa k and omega yet, right? So we need to say when this holds. If there exists an omega that should just be smaller than infinity, so a finite real number, and a kappa that should be element, maybe, yeah, I directly say it's smaller than 1. This is binding. This kappa is actually an upper bound on these kappas, such that for all indices, for all iterates zk, and also for all z element in Rn. So this is a bit nasty, so for all other z as well. so we will need both of them in the assumptions, holds the following, and then there will be two conditions. And these two conditions are first a kind of Lipschitz condition, which is bounding the distance between two Jacobians. So maybe I should first write it. So here we have mk to the minus 1 j, and here I'm, as I said, lazy by just stating that here. So the distance between the two Jacobians at two different points. Jacobian, I should define just to be sure. J of z is defined to be dr by dz at the point z. So that's a matrix, a square matrix. This Jacobian should be smaller than omega times the distance of zk and z. Please note that I could also take just another y here, yeah? But I want to be at least a bit specific because I don't need it for all. I need to just have it at the points where I visit and then for all others around it. So this should hold, and I call it Lipschitz condition. Or sometimes I call it the omega condition. So that's just because we use the constant omega here. And the other condition that we need to hold is similar, actually. It looks very similar, but it's a condition on the distance between this thing, J, the Jacobian, minus the approximate matrix. So the matrix that we actually use in our Newton iteration. And that should be bounded by kappa k, and this should be smaller than kappa. And the kappa, as you remember, should be smaller than 1. So this is definitely smaller than 1. And this is what we sometimes call compatibility condition, because it's, so to say, the compatibility of the matrix with the true Jacobian. And of course, to be clear, we could also just call it the kappa condition. So these two things need to hold, but that's not all, because that just is, these are some assumptions on the function. And I should say R is element in C2, right? Otherwise we wouldn't have the Jacobian. It's also a bit lazy. C1, and actually C1 would be enough. So let's state C1, and we will have the rest. This is Lipschitz continuity, actually. So it's a bit more than just C1. But this is not all that we will need, because so far we have just a contraction. This will be enough to prove this contraction reality, but we didn't specify yet that this whole thing will converge. Maybe I should say here, zk converges to z star, and contraction rate, this contraction inequality holds. If these things exist, so if they exist, these omega and kappa, and they hold for all iterates, and also if we start the iteration close enough to the solution. So that's the last thing. So, and if z0 minus z star in the norm is smaller, and now it should be smaller, maybe I should directly tell you, it should be smaller than some distance, which is ensuring that this contraction factor is already smaller than 1 from the beginning. So we basically have to invert that statement, which yields, if you think of it, we isolate that 1. I think I copy it and then I explain it afterwards. So we have here 2 divided by omega times 1 minus kappa. So maybe I should just to state what this means. It means that kappa plus omega half times z0 minus z star is smaller. I need not inequality, but only strict inequality is smaller than 1. So that's what I need. And this will, of course, ensure that the first contraction factor is already smaller than 1. So the first iterate already contracts. So what does it also mean? It means that the distance is close enough, I z star is close to z star. Okay, so this is a bit a very quick statement of a theorem that can be made much more complicated if you like, and also a bit more general. But I want to make a few remarks first. One simple note is that this whole statement would actually also apply to a Newton's method. What would be, for a Newton's method, we would have this J and that M being the same. So for a Newton's method, we would have a kappa equals 0. Maybe I say for exact Newton, kappa equals 0. So all the kappas can be chosen to be 0. And in the more general case that we regard here, namely where we have a contraction with some approximate matrix M, we could have a kappa that is non-trivially above 0, but it should be below 1. Otherwise, we get into problems. I think I will not repeat the little proof, which will be relatively straightforward based on just integral formulas. I think that's not necessary here. It's done also, it was done in another lecture that was happening here at the same place in the numerical optimization lecture. But I want to illustrate briefly what this means, so to say. Yeah? So the reasoning, maybe I should put it into a two-dimensional space. Yeah? So think of having two components of Z. Yeah? This is a bit misleading because this index is now the component index, so I make something to make it a different index. So this would be two different axes of the whole setup. We would have our minimum here, yeah? Minimum or the root of our function R. And at some point we would need our Z0, so that will be one place. As I said, this contraction inequality at the top, yeah, that one is something that we can prove based on these two assumptions alone, very quickly. And together with this assumption that the initial contraction factor is smaller than 1, because this distance here is so the Z0 is close enough to the Z star in a ball that is basically defined by that inequality. Yeah? So if you're inside that ball, then you know that the contraction rate will be already linear and smaller than this thing, or exactly equal to this thing, which is smaller than 1. So you know that afterwards the next iterate Z1 will be inside a ball that is smaller, and then you go on. I mean, there's always this contraction rate that's getting only smaller because your distances here get smaller, so this whole thing can only get smaller, and so the convergence very quickly follows. Huh? So you get contracting balls. It's just all based on linear convergence, and that's what this inequality basically says. Yeah, so as I said, I don't show how I go from these two inequalities to the contraction inequality here, but this can be straightforwardly copied in the proof if you like. Is there anyone who wants to see that because you find it important or interesting and you don't believe me? No? Okay, it's okay. So then I would like to make just a few remarks, so that you know about the story. There is books about Newton's method in general. I can recommend one book by a person called Diehl on Newton's method. You will find a similar version of this theorem in that book. There's also PhD thesis of Hans-Georg Bock in 1987, where you find a very similar version to this. And sometimes some of these conditions are slightly weaker formulated. So there's a weaker variant, which is nearly as easy as this one to prove, where you make a slightly less stringent assumption, and that is actually the assumption which I should directly tell you. For the first one, for the omega, you would just say, I can actually reply, have this distance j, zk, the same thing that we have, but I need to compare it only with all the j's which are on a straight line between the point zk and the point z star. So here I have actually, how do I put it, zk plus t times z star minus zk. Okay, and then I close this bracket, and then I close the other bracket, and then I put the norm here, right? So this is replacing this z that I put there for laziness. And then you actually say this should be smaller than omega times t times z k minus z star squared. Why do I say squared here? Because, I mean, that z, this distance appears also in this distance. So, and the t also appears here, so that's why I have a t and a squared here. But it's actually just a slightly weaker assumption than this, because I only need to check this whole thing on the line between these points. Now, while before I needed to check it on every point z in the whole space. So that's definitely weaker. In practice, it's anyway difficult to check these things. But the kappa condition in this slightly weaker form would be that I also only test this. Oh, sorry, I actually had I forgot something here. I forgot even the multiplication with z star minus zk here. So, and then the norm. Okay. Okay, so then you see this t times this without a square is due to that, and the other comes due to this distance here. So please note that this is a vector that you multiply to this metric. So this whole thing here is a vector in the same norm as z. Okay, and the other condition was, as I said, this distance between the true matrix, the true Jacobian and the approximate one. But in principle, and for the proof, it would be enough to check this distance only in the directions in which we actually move. So you could also just multiply it with the direction in which you will move, or in the distance direction actually, and then say this is smaller than kappa k times the distance zk minus z star. So that would be a slightly weaker formulation, which will lead to the same results. So please also note what this means is that this matrix needs to be similar. These two matrices need to be similar only in a specific direction, namely this one. Yes?
Wouldn't that have to be the absolute value of t that had on the right side in the calculation?
Yes. Yeah. Actually, I should also say for all t, it's only restricted to 0 and 1. I should have said that. I don't have it in my script. Yeah, it's good. I should just specify it. I'm only interested in the points which really, this is generating the points on the line between zk and z star. Yeah, so it's only for positive and smaller than 1. Thank you for the remark. Okay. So that's a weaker variant that in some cases where you might not be able to prove this, you could try to prove that, and then you also would get convergence. So that's one thing. That's sometimes preferred. I just wanted you to know about it, but I find the above thing already complicated enough, so that's why I prefer this for the presentation. So please keep in mind what it really means is a rescaled version of similarity between these two matrices. I just multiplied with this inverse because it's making it unitless. If I would multiply my whole residual function with some factor, 10,000, this would make this factor disappear again. And the same thing here. I have a distance between j and j at different locations. So this is nothing else than Lipschitz continuity of the Jacobian, which actually is something we could always have. At least locally, this is a very weak assumption. Any C2 function will have this property. Okay. There is some interest about a property that I also wanted to share with you that's called affine invariance. So 2.3 is about affine invariance. and it's a property that I can relatively easily define and which I should motivate a bit. So the motivation is, or what does it mean? Affine invariance of a method, of an algorithm, is that if you rescale your system, your variables or your equations, with some linear but invertible map, so you basically do a basis transformation of the space of variables or of your residuals, that then your method will yield equivalent iterates. That's something that is sometimes the case and sometimes not the case for methods. And we like it, usually if it is the case, because very often scaling of a problem, scaling is a difficult thing, in particular if you have several hundreds of thousands of variables. Each of these variables needs to get the right scale, and maybe even mix terms between these variables need to be regarded, and also the residuals could be rescaled. And so affine invariance basically means that if you have RZ, so a root finding problem, and you apply a method to it, then it will lead to some iterates Z0, Z1, Z2, so with some method. And now you could actually apply you can rescale or a coordinate change. You could just say I make a coordinate change of my problem. And what does it mean, a coordinate change? This R is a function from Rn to Rn. So I could change both the output of this, and let's do it how we do it in the script. So I just say I have a new R, which I call R tilde, and my new variable is Y. It's not Z anymore. And I say this thing is just defined to be something where I turn my my residual R with some matrix A, which is invertible. And I also make sure that my residual here is B plus matrix B times Y. Well, now this B is also an invertible matrix, and this should now be equal to 0. So that is the new problem, and that's a definition. And A and B are element in Rn cross n, and invertible matrices. So that's the only thing that I need to assume here. And then you obviously see that I have a new, an equivalent system, right? So think of, for example, you have something that why don't we think of our problem here? We just had something where we say we work in Cartesian space. So what would happen if you now rescale the velocity, or you change the coordinate system from xy to something like this? So you just align your axes a little bit different. That is what you reflect with these input changes. And an output change is a bit more complicated in that context, because we didn't really specify the residual yet. But if you also think of something you want to maybe throw two balls and they should exactly meet at the same point, that would be a root finding problem. Then you could also look at this point where they should exactly meet in a rotated coordinate frame. Instead of this, you could rotate it like that. You could measure different directions in the space in millimeters and the other in meter or whatever. So you could do nasty things, which sound a bit nasty in this context, but in context where you have units of one quantity is in meters, the other is in seconds, it's very logical that you cannot easily decide which of the units you should take, so to say. So it's a very natural question to ask. If you say, apply now the same method to the problem, what iterates will it generate? And what you would like is that if you start at y0, which should be actually the inverse of that, so if that should be z0, so I should just invert that, which means I put a b to the -1 and then z0 minus b, right? I think this will yield the same thing. So if I start with that initial value, then it will yield y1, y2, and so on, which are just the rotated versions of with the same formula as this one. So if these things are equal to the rotated versions of the z values, then you say it's an affine invariant method, and otherwise not. Okay, so affine invariance is something we like, and I just wanted to mention that this condition exists. Affine invariance is relatively easy to understand as a principle. Its meaning is that if you rescale your problem, if you choose different coordinate systems, at least as long as they are just linear transformations, your methods will behave the same. And now the good thing, and I should mention that, Isaac Newton is affine invariant. So that's one of the strong points of Isaac Newton. Really, that's one of the things that we like. And maybe the proof, if you want a proof, why shouldn't we do a proof, is we just look at zk plus 1 equals zk minus j of zk to the minus 1 times r of zk, right? So this is the iteration. So now I want to translate that equation to something which has to do with yk plus 1, and it should, when we apply the new method to it, then we will have here a j tilde of yk times r tilde of yk, right? So that's what the other iteration will be, and now we need to just compute, based on this definition, what are the j tilde and the r tilde. Yeah, the r tilde we know already, but what is the j tilde of y? It is generally, I mean, just the chain rule, so it will be a times the Jacobian of the z. So j times the Jacobian of the z, which is actually j of b plus b times y, right? And then the inner derivative is due to this b is a matrix multiplication with a b. And here I forgot the minus 1, of course. So now this is just a bracket, which I wanted. So how are these two things related? So let me just see. What happens if we insert that formula here? Then we will get yk plus 1 equals yk minus. Okay, and here we have now b to the minus 1. Because of that, then j at b plus b yk to the minus 1. And here we have an a to the minus 1 because of that one. And here now we insert the definition that we had here. Here we have an a times r, and it's evaluated at z, which is actually b plus b yk, right? And that's it. Okay, so what will happen here is that we can just see that these two things cancel. They are getting a unit matrix. And what we also see is that this thing here is exactly, I mean, the yk, if it started, there was this relation zk equals b plus b times yk. So if we assume that it was already the scaled or the rescaled variant, right? So if this zk and the yk are related with the same formula that we want, then this term would be actually the same as jzk to the minus 1 times r of zk, which is what we had here. Yeah. But now you see that how can I prove it, so to say? And what I want to prove is actually that yk plus 1 is equal to b plus b times zk plus 1. So this is something I don't know yet, but this is what I would like to prove. And if I have shown that this is the case, then I'm ready. So let's just look at this. So we know already that these two are related by, oh, that's the wrong direction. Yk, zk. So this is the relation that we can use, and now we can either insert one into the other. So it's easier probably to insert this thing into the formula that we have here. So let's just insert everything here. So we have this one is b plus b yk plus 1, which is given by b plus b times yk plus, so I just insert everything here that I have here into that other equation. It's getting a bit long and tedious maybe, but let's just do it correctly. minus. Yeah? So I get now this thing. It's multiplied with a b, so that's moved away, and I get a j zk to the minus 1 times r of zk. And now I'm ready, actually, aren't I? Because this is actually the same thing due to the assumption as zk minus j zk to the minus 1 r of zk. Okay, and that's exactly what I wanted, which is also the next step here. So you see the two formulations, rescaling the whole system didn't give you different results. Yeah? So that was a slightly improvised proof, but roughly speaking, no, not roughly speaking, this is one iteration, this is the other. What we have proven is that if you start with this equality, I mean with the same iterate, so to say, in a scaled coordinate version, that even this other iteration in the y space gives you the same iterate in this rotated frame. Yeah? So it's just, I mean, it's complicated formulas, you just need to keep the overview, but there's nothing deep in it. Yeah? It's just rescaling. This is a very beautiful property, I should say. Yeah? And so it's not the case for many methods that you might see in the literature, and so it's a good question that you should ask yourself when you look at a numerical method for nonlinear equation systems. Is it a fine invariant or not? Newton's method is. Some other optimization methods that we will learn about, like Gauss-Newton's method, they are also a fine invariant, but some others are not. Okay. So, there's one example of methods that is not so much a fine invariant. Maybe I should already make this remark here. If you do have an optimization problem, an unconstrained optimization problem, yeah, then you could just say, I mean, unconstrained optimization is something we don't treat here, but I just wanted to say what it is. It is just minimizing a function f of x, scalar function subject to x in Rn. Yeah? It's not subject, there is no optimization. And there are the first order necessary conditions of optimality. They just say the gradient of f at some point x star should be equal to 0. Yeah? And so now, if I just define, so to say, z to be the x and the r of z to be nabla f of x, yeah? So that could be one way to define a root finding problem, then I could try to solve this optimization problem with a Newton's method. Yeah? So if I think of it, what would be the dr by dz at some point z? It's actually the second derivative of this whole thing, and we call that the Hessian matrix. Second derivative of f turns out to be symmetric, which is something we didn't assume in all the other discussions, but it's anyway a special case of our optimization. So Isaac Newton in this context would be the following. It would just say zk plus 1 is equal to zk minus the second derivative of our function f at zk to the minus 1 times the gradient of f at zk. So that would be the exact Newton method for optimization. That's a very easy to understand and to implement method. But very often we do other things, and one thing that people very often think of as a very intuitive method is that you just think of your, if you have here your variables z1, z2 in two-dimensional space, yeah, you might have a minimum somewhere, and now you will typically have level lines around it. We will discuss it in a minute. And one other method that you could think of is when you are at some point, you want to go down. Right? That's what we call the gradient method. We could just go down a bit. And we go down only a very little bit. And usually we can implement that by just going into the direction of the negative gradient, which makes this matrix basically a scaled unit matrix. So with mk being some matrix or some coefficient alpha times a unit matrix, this gets zk plus 1 equals zk minus 1 over alpha k, right, times the gradient f at zk. You see that? because we have the inverse of m instead of the exact Jacobian for Newton type. And so if this alpha is very big, then these steps will be very small, and then you will basically go the path down to the minimum, which we call the path of steepest descent. It's a bit like an ODE solution that just rolls downwards all the time. So it's very intuitive, but this method is unfortunately not affine invariant, and if I would just change the scale of my variable system, unfortunately the direction of the steepest descent is depending on my coordinate change. Yeah? So the steepest descent direction is something that is very, very sensitive to scaling. So it's not an affine invariant. Just as one example of a not affine invariant method. So, by the way, this is by definition, because we have proven it before, it is affine invariant, right? So, whichever coordinate system you look at, this method, it is affine invariant. This method, it's not. Just to have two examples of affine invariance already in the context of optimization. And for whom this was a very fast step from Newton to optimization, I would like to say sorry, but I think this is something you probably have seen before at school. And so it's exactly a root finding problem of the dimension n in n variables. So in principle, it's exactly the same framework that we have here in optimization. And in bottom line, we will go very much in this direction of solving systems of this form or similar systems. For constraint optimization, it gets slightly more difficult. But the general framework of Newton type iterations for root finding is always the same, and that's why I decided to put this to the front of this whole lecture, so we get familiar with Newton's method before we apply it in different contexts. And in order to make you even more familiar with Newton's method, I want to discuss after the break another concept, or I want to discuss tight conditions for local convergence of Newton type methods. So, which are, if you remember what these conditions are, they are just sufficient, right? So they are very lazy. At some point I even said, yeah, let's just assume it for all the z's here. This Lipschitz condition is particularly nasty, right? Because it's specifying it for the whole space, right? So it's completely exaggerated. But there is a very tight and local condition for local convergence, and if that is satisfied, then you will have local convergence. If that's not satisfied, you will not have local convergence. So it's important to just look at a tighter version of that, which is, however, only based on linearization, so it will only give you linear convergence or divergence. And afterwards, I want to also discuss one topic which is called globalization, which is related to the fact that this whole assumptions, the set of assumptions that we made, is based on being initially close enough to the solution, which, of course, this is the point you don't know, right? That's the point you want to find. So how do you know that you're close enough? You never know. So in practice, you will have to do some things like make your steps possibly shorter and hopefully reach a point where you get to this local contraction. And before you are there, you need something that we call globalization. And for that, I want to give you already one simple example of a method so that you could, after this lecture, actually implement Newton's method yourself and understand it also. Let's have 10 minutes break. We continue 10 past 3. Okay, so let's continue. And as I promised, I would like to go to tight conditions for local convergence. So to discuss it a bit before we start, I just want to say that if you are very close to a point that you know is a solution, which is of course a quite artificial condition, right? But if you are very close to this point, you would like to know if a specific Newton type method would converge to that point or not. And I want to base this analysis only on local information, that means on derivatives at this single point. And it turns out that this really gives us a tight criterion for convergence or not convergence, which is based mostly on the kappa. Tight conditions for local convergence. And so maybe I should first recall that the condition that we had until now for making some Newton type method converge was that our initial condition is Z0 minus Z star should be small enough, and you remember this was smaller than, what did we say, 2 divided by omega 1 minus kappa, right? And so if you make this small enough, I mean very, very close, then, and this kappa was smaller than 1, then independent of how big this omega was, it will be possible to meet it. But of course this kappa could be above 1, and then you have a problem. Our theorem from before would not even be able to tell us if we start at the solution, if we would stay at that solution, or if we would diverge from it away. And this is what we want to overcome. We want to find, so to say, the best possible kappa. Yeah? And I call it, the aim of this section is, so to say, find what we could call kappa exact. Because the kappa that is exact is actually giving us the asymptotic linear convergence rate. Asymptotic linear convergence rate. Maybe I should also say, why do I say it's the asymptotic rate? Because in our other condition, and maybe I should say this zk plus 1 minus z star, yeah, that will be smaller than something where you remember there was the kappa plus omega half, but this thing will go to 0 anyway when we are close enough. So the only thing that remains is really this kappa, or we call it kappa k to include the possibility of an index. But if these kappa k's are, if we cannot prove that they are smaller than 1, then we would have a problem, and we would not even be able to prove local convergence for a method that might actually locally converge. And so the kappa exact is the asymptotic linear contraction rate of an iteration. And we have to restrict our analysis to some special case. And the restriction is that we will choose mk only as something which is a function of zk. And this function needs to be even differentiable, C1. Yeah, so we want to have a method, Newton's method would be part of it. Newton type methods like Gauss-Newton would be part of it as well. Also a constant matrix would still be, if we always use the same, then it's of course a function. But what would be not covered by this theorem is a randomly chosen matrix M, for example, which could in principle be covered by the other theorem where you just choose a new mk in every iteration. But here we need to have it a function of z. Yeah, but also a constant is a function of z, right? So anything that's not just random or jumping from iteration to iteration. And this maybe I should say covers Newton, a method that we will later learn, Gauss-Newton. It covers also constant Jacobian, and some other methods. How do we go? We will actually just look at the iteration as a dynamic system. And so the idea is that we just look at a dynamic system where we say, actually what we have is zk plus 1 is equal to zk minus, and now I write already this expression, m of zk to the minus 1 r of zk. So that's a dynamic system, and I could define this whole thing as a function which maps at zk to the next zk plus 1. And I call this function already here g of zk. So what I get then is basically the iteration zk plus 1 is equal to g of zk. And that is the iteration that we can now analyze with normal means from linear systems theory. or from nonlinear systems theory actually, because it's a nonlinear iteration. But it's very easy to understand a basic theorem which I don't want to prove, but which I call linear stability analysis, and that tells us actually when this dynamic system is stable at some fixed point. So this is a lemma 2.5 that I want to share with you, 2.5, and I call it linear stability analysis. And it's pretty straightforward, but I just want to make sure that we have the notation and so on, right? So regard zk plus 1 equals g of zk. And a fixed point, so now we have a fixed point of that. Fixed point z star with what should the fixed point satisfy? It should just satisfy this relation. And G should be C1, differentiable, so that we can compute its derivatives. And so now we can actually say if the spectral radius of the Jacobian of this function G, this Jacobian at the fixed point, if this spectral radius, so maybe I should call it spectral radius. So if all the eigenvalues, the modulus of the eigenvalues, if the spectral radius of this Jacobian is smaller than 1, then maybe I should even define it. No, I don't define it. Then zk converge to z star if z0 minus z star is small enough. So small enough. I don't specify it. I just want to allow that I'm extremely close to the initial point. Just want to look at the very asymptotic rate at the very end. Then it converges. If, on the other hand, the spectral radius dg dz z star is bigger than 1, it diverges. At least for some z0 in the neighborhood, in any neighborhood of this point. Z star. So whatever you do, if the spectral radius is bigger than 1, there will be some z0 that will diverge, as long as you don't start exactly in Z star, because then, of course, it remains a fixed point, but it's an unstable fixed point. So the reasoning is roughly, if I have this two-dimensional space here, I have my point Z star here, and I'm allowed to choose a very, very small region, but because I'm at the blackboard, I make it already big, but imagine this is infinitely small. So if there's some eigenvalue of this Jacobian that's bigger than 1, then there is some point here in this neighborhood, even if I make it very small, where after one iteration, actually where I will grow away from this. And on the other hand, if my spectral radius is smaller than 1, then I will contract. So now I didn't really define, maybe, well, you might not be familiar with the spectral radius. So rho of A is defined as the maximum of all the eigenvalues. And it's actually the maximum of the modulus of the eigenvalues. Lambda is eigenvalue of A. So that's what we really define it. So if you think of the spectrum of a matrix in the complex plane, real and imaginary part, then there might be spectrum. For real valued matrices, it's usually symmetric. But so this could be a typical spectrum of this matrix A, and as long as the spectrum is inside the unit matrix, you have contraction, but if as long at the moment that there is one eigenvalue out, then you get divergence. So it's very similar to linear systems analysis. It's just tight in the sense that if it's smaller than 1, then you will converge. If it's bigger than 1, then you will diverge. And if it's equal to 1, I should say, we don't know. Because then linearizations don't tell us any, we need higher order derivatives or more involved theory in order to prove stability or not. But that's beyond our interest here, and it's much too specific. Yeah? But it's tight in the sense that the numbers where this is exactly 1, that's a very rare occasion, of course. Okay, so you get a theorem that I will not prove. This lemma, I think, is pretty straightforward. It's something like just contracting or not. Maybe to visualize it, and I like to visualize it, if you have Z here, and your function, maybe I should say, yeah, I think that's good. So you have my axis, and then I have a function, maybe g of Z here. This is exactly the 45-degree line. Then here's a fixed point of that. So that would be the point Z star. And this theorem basically says if the slope, I mean for one dimension, it would be if this slope is smaller than 1, you will converge. If the slope is bigger than 1, then you will diverge. Yeah? And it's very easy to understand why, because if you have the g Z, you will have to evaluate it at some point in the neighborhood. If you evaluate at this point, I mean, it's always nice to have the point visualized on the diagonal. I mean, every point at the bottom has also a representation here at the diagonal, but its function value is then this one. Then you find a new point on the diagonal, and here you see that it very quickly contracts. Also, if you're here, if you would start at this point, you evaluate the function that corresponds to this value here. You evaluate the function again, and you see you very quickly converge, while you would diverge if the slope would be different. Of course, in higher dimensions, this little two-dimensional plot wouldn't help you, but it's pretty intuitive, because a linearized system gives you a good approximation. Locally, we will have that zk plus 1 minus z star is approximately equal to dg by dz z star times zk minus z star plus higher order terms. But if you think of this as the local, that's the Taylor series of G in the neighborhood, then you see it's nearly like a linear system where this matrix plays the role of the system matrix. And if you take the powers of this matrix, many powers, then you see at some point the largest modulus eigenvalue will survive, and that's the one that decides on convergence or not. So different perspectives on the same thing. Just to visualize that lemma, is there any question about this lemma, which I basically assume from linear systems theory? I think for me it's straightforward, but I don't know if it's something that everyone finds intuitive or not. Is it okay? Or do I need to discuss it more? No? Good. Okay. So I already told the main story, namely that I want to now apply this lemma to that specific function g. And that's what I will do. But I will directly call it a theorem, even though it's just a corollary if you think of it. Move this down now. And the theorem is called 2.6. And it will say that we regard now the iteration zk plus 1 equals zk minus m of zk to the minus 1 times r of zk with m C1 and R C2, just to be on the safe side. We could probably weaken these assumptions a bit. And then we regard also with R of Z star. So that means actually it is a fixed point, because if this is 0, then there is no change anymore and you stay there. But I will also assume, of course, I should say M Z star should be invertible. I mean, the M should be invertible everywhere, but at least in the neighborhood it should be invertible. And that will be covered by this assumption. And now we say if the eigenvalues, or maybe I should directly say if kappa exact, which I define to be the spectral radius of the matrix that I get by linearizing this map. But by linearizing this map, it means I need to take the derivative here. That's a unit matrix minus M Z star to the minus 1 times d R d Z at Z star. So this is the matrix I need to look at. And that's the spectral radius. If K exact is smaller than 1, locally it contracts, iteration contracts, locally contracts with rate, with the contraction with the linear rate kappa exact. So that's the linear contraction rate. You can not converge faster then. And if K exact is bigger than 1, it diverges. So that sounds easy and nice, but actually it might look a bit too easy if you think of it. The proof for this is straightforward. It's apply lemma 2.5 with G of Z defined to be Z minus mz to the minus 1 R of Z. And noting one thing, and that is the only non-trivial part, namely dg by dz of z. It is also trivial, I should say, but anyway, is the unit matrix, right? Minus, and now I should say, here I would have first the derivative of this whole thing by z, right? I will just write it like that, applied to R of z, and then here is minus m z to the minus 1 times R, and here's the Jacobian dr at dz at z. Okay, so I don't evaluate that expression because it's a bit complicated. But if I'm at the steady state, or at this at the point where I'm actually interested in it, I see that this residual here is 0, so this whole term that I could compute because it's a differentiable and invertible matrix M, but I don't want to compute it because it's multiplied with 0, it's anyway vanishing, so I get this minus 0 minus m of z star to the minus 1 and then dr of dz z star. And that's already the proof. You see, it gets a bit simple because this complicated derivative of the matrix inverse is just vanishing. Yeah, so it's really this matrix that I need to look at, and now I should say, what is this matrix really? How do I actually interpret this matrix? So maybe I should also call this thing J, like the Jacobian that we did at some point. So let me just look at what is this thing, I minus m of z star to the minus 1 times j of z star. What is it? It's actually not so different to the thing that we had in the kappa condition. namely, we could just write it the following way. I mean, I just augment this whole thing with an m z star to the minus 1. And then this unit matrix will just be m z star, right? And then this thing will be just minus j z star. So you see, again, it's something that is just the difference between my Jacobian approximation, put a minus sign here, this m, and the j, which is the true Jacobian at my solution point, but multiplied with this m to the minus 1. So this is a basic relation, so it's actually kappa exact measures again, and that's why it's related to kappa, measures distance between m and j. There's a question.
Yes, I just don't really get the point why R of z is 0.
At that star only, at that star.
But in the line above it's not that star. Oh, okay.
Yes, exactly. So here it's not that star, so that's a general expression, but once I insert that star, which by assumption it is 0, then this term is 0. This is something, but it's finite and it's well defined. I multiply it with 0, it's 0. That's why I need differentiability of this m, because otherwise it could be infinite and then I would get some problems. Okay. Of course, I would invite anyone who has a very theoretical mind to think of what would be the minimal assumptions on M. Probably it's just Lipschitz continuity. That should be enough. But I didn't check it in detail yet. Okay. So this is like the basic observations. So we get a tight condition on our distance. So if this matrix here that we see here has a spectral radius smaller than 1, we are fine. And if it's bigger than 1, we are not fine. And so I would like to ask you a question. So what is for exact Newton, what is this kappa exact? What will we have? Yes?
0, isn't it?
Absolutely, yeah. So we will have kappa exact equals 0. What does it mean?
That our approximation of the Jacobian is
Yes. And it basically, from this theorem, I mean, it just says it will locally contract with a linear rate, kappa exact. But of course, if kappa exact is 0, then the nonlinear terms will matter, and then it's actually quadratic convergence. But from the linear perspective, it's linear convergence with 0 contraction rate. So you could say that the contraction rate, if you look at it from the perspective of linear convergence of a Newton's method, will get better and better because it's quadratic. So it's covering also Newton's method, but it's not really designed. And the wording of it is not really designed for Newton's method. Maybe I should also say a few other words which are maybe interesting to some of you. Any iteration which has this property that the m at the solution gets equal to the true Jacobian will have this property that kappa exact is 0 and that you get actually quadratic convergence. So Newton's method is not the only method that you can design that has quadratic convergence. You could design other methods, and sometimes people invent Newton-type methods, which are not Newton's method, but still have quadratic convergence. But they need to have this property, that these two matrices need to be the same at the solution. So it doesn't really matter if you're, maybe I should say this in a few words. So here you have R of Z. And it doesn't matter actually that you have the exact tangent at some non-exact iterates. The only thing that you need is that once you approach the point, your tangents get right. Yeah? So you could have some points which are maybe bad approximations, bad tangents here, but once you come close, they get really tangent. So maybe for the experts, Gauss-Newton's method, when you solve a zero residual problem, is of this form, for example. It's different than Newton, but it's if you solve it for a zero residual problem, it will have quadratic convergence also. And there are many, or some other examples I could discuss if someone has interest. I think I still want to dig into the next and last part of this chapter. And while we discussed local convergence until now, I want to now go to the other extreme, and that is what happens if you're very far from the solution and you want to analyze, or not analyze, actually you want to modify your method so that you would still be able to converge, even though you're not local, close to your local solution. So that is what we call globalization. It's like section 2.5. And so the question is, what for z star minus z star big? So if this is a very big distance, what will you do? And there are many different ways of dealing with this, but one, and I think the more widespread class of methods, they use some form of merit function. So they are already very much in the spirit of optimization, but I will actually directly present it for Newton-type methods in general, or actually for Newton's method in this example. But the idea is actually regard what we call a merit function that shows, so to say, how good an iterate is, and ensure that this merit function only gets smaller. That measures the error, actually, and is only reduced. During the iterations. And not the standard, but the globalized iterations. And I should say that this is, of course, very sloppy. And we will, there are many different ways of globalization, but one way that I can explain most easily is an example. And this merit function, maybe I should call this merit function v of z. Yeah? So v of z is a function from Rn to R. And this merit function is designed so that if you're at a solution, you somehow have at least a minimum of this merit function. And so the merit function that I want to look at with you is this one where you just say, actually, I can take the squared norm of my residuals. Right? And if I'm at 0, then I'm happy, because then my merit function will be 0. So this v of z is always bigger than 0, and v of z star, I don't know where the v z star is, but if I have a solution, then my r of z star will be 0, and then the squared residual will also be 0. So this would be such a merit function. And if you think of your root finding problem in this high dimensional space, Z1 and Z2, from this perspective, then it actually becomes an optimization problem. And at this point, Z star, you have the minimum, which is 0. And at other places, you might have higher values. And this is like, I draw level sets. So they're getting bigger. Higher values of this function v. V of z being constant at these values. Here it's 0, and here it's a bit bigger, here it's more bigger, and so on. So basically, you created a valley, a function with a valley, where the deepest point is z star. Of course, because it's a nonlinear problem, there could be another point somewhere else. It would be also a 0 point, could be another solution z star, but I'm not regarding that case at the moment. I should also say that there are many other possibilities, so there could be other local minima which are not 0 at other places. But at least when you're in the neighborhood of some of these points, but this can be now a larger neighborhood, now you could try to ensure that you always go, so to say, into a level set which is a bit smaller. And so if you can only decrease this v during your iterations, you can actually make sure that your function will at least be decreased. Yeah? So the aim would be is that zk plus 1 should be somehow smaller than v of zk. By modification. So you make a modification of your Newton step. Possibly there are many different ways, and I will only explain one way. One example. And this one example is a so-called line search. And it's a line search with Amio backtracking. Amio backtracking, so just for the experts, I give the name, so to say, directly at the beginning. Backtracking, line search for exact Newton. So that's the simplest way of globalization. And I can only do it for exact Newton in this form in which I will present it. And it will look as follows. You define zk plus 1 is equal to zk minus, and now I modify the step by making it smaller, and I will actually call it alpha k times, what do I have here? The exact Jacobian zk to the minus 1, and here I have r of zk. So with alpha k element in 0 and 1. So it should be something that makes my steps smaller and ensure that the Amio condition, as we call it, I will satisfy. I will state it in a minute. Satisfied. What is this Amio condition? It says actually that the function v at the value k plus 1 should be smaller or equal to the value that this function had before. But you remember, I mean, we really want to go down, so we want to really go from one level set to a lower one, but by a margin, and the margin that we apply here is something that depends on the step length. Just want to have the right notation, the gamma, alpha k, or alpha times gamma times the gradient of v at zk times the step that we take, which is actually, in this case, and I should be sure that I use the right notation, I call it pz, so that's a bit nasty, but maybe I define it then. This is p of zk, so that is just a definition of this step, p of zk. So, this condition for some gamma which is between 0 and 1/2. So what this condition ensures, and I give directly the index k here. So I want to actually be in a picture. If I have my iterate zk somewhere, and I will have my future iterate zk plus 1 somewhere, and I have here the direction that's spanned by modifying alpha, because I go from zk into the direction of minus p. Oh, sorry, I think I should. This p should be with a minus sign to be consistent with the script, right? So here's a minus already, and here I can have a plus. So now this would be my function v of zk plus alpha times p of zk. So if I can evaluate my function at the point alpha equals 0, I could also evaluate it at some point, maybe here would be alpha equals 1. And what I want to ensure is that I'm actually somehow not only deeper than this point, and I know that I have the tangent here, but I will actually, this would be a Taylor series if there would be no gamma, but because the gamma is something between 0 and a half, it's something between here and half of the slope. So it's something here, and any point that is below that will be acceptable. And so that is what this Amio condition satisfies, and you immediately see that for small enough alpha, if you move close enough to your original point, if you choose this small enough, you will be below this slope because you approach the tangent. Yeah, and because this gamma isn't chosen as 1, but significantly lower than 1, you will have a margin here. And so it will be possible to actually stay below this line, and by staying below that line, you will ensure that you really go down. And that allows to prove that you converge to a local minimum of that function v. So I didn't specify the algorithm, but I should say what you do. Choose alpha k such that it satisfies the Amio condition. Maybe I call it 1. Is satisfied trying, and now you try it actually, trying alpha k, alpha equals 1 first, then alpha k equals beta, no, maybe I should, equals beta, with beta something which is between 0 and 1, so it's a number that's smaller than 1, then alpha equals beta square, and so on. So you actually contract geometrically, you make your step smaller, and if you started, for example, here with alpha equals 1, you see it's not satisfied. Now you contract, for example, by 1/2, or maybe you contract a bit. Here it's not satisfied, you contract further. Here it will be satisfied. So actually it is the largest, alpha k is actually the maximum from all the values 1, beta squared, so that beta to the power of k satisfies the Amio. So that's a very sloppy notation, but I think in words it's clear. You try the longest first. If it doesn't satisfy Amio, you try one smaller. If at the first time that it satisfies the Amio condition, you will actually stop, and then you have found a point that satisfies it. And of course, there's something I didn't really specify, and I think I should say it. We didn't actually specify that the direction in which we move is a direction which actually moves us down. I just said I take the Newton step, and I somehow assumed that I would go down, which I didn't really prove. So I need to prove it. So first of all, so P of Z, which I defined as being minus J of Z to the -1 RZ, right? So I want to say, is this thing a descent direction? So does it actually lead us down? And it does. And how do we check it? We can check the gradient of V at some point Z, and we can check if this gradient, if we put the scalar product with this P of Z, if that's a directional derivative of V, if that is negative, then we are done. So what is it? So nabla V is something we can just compute based on its definition. And P of Z we can also compute. So what is nabla V? Nabla V is actually, let me compute it. It's the Jacobian of R times R, right? So here's a transpose. So it's actually R of Z times D. Maybe I directly put the Jacobian, J of Z, transpose. And because of the factor 1/2, this is actually cancelled. because I have it twice. So that would be the expression for the gradient of v. And p of z is minus j of z to the minus 1 times r of z. Okay, and now I see that if I multiply these two things, this is getting a j, it's multiplied with that, it's compensating each other, and what we get is minus r z transpose j z to the minus 1 r z, which is actually equal to minus 2 times v of z. And that is definitely negative, because v of z is always positive. You see? So indeed, we get the descent direction, and because we always have a descent direction, we can ensure with this method that there exists a non-trivial step, I mean non-zero step, alpha, that will lead us down. And with this little modification, you can already practically start implementing Newton's method if you like. We will go into more details a bit later, but that is roughly the idea of globalization and already a practical variant that helps you for many problems. There's a question.
Two questions, actually.
Yes, two questions.
First question, shouldn't that be smaller equal to 0, not smaller 1?
Yes, for z not being z star, it's actually strictly smaller than 0, because when you don't have a solution, you have a positive value.
And another question, I understood you in a way that you said that the tangent that you evaluate is somehow the upper bound, like how far you can go down, but this is only true for convex functions, right?
No. It's the reasoning is the following. So this Amio condition, which is this statement here, is a modification of first order Taylor series of my function where I introduced this gamma. Because, I mean, what this is, it's a Taylor expansion in the direction p with alpha as a scaling parameter. So what I regard here, I think I say it here, right? So what I regard is the function v at zk plus alpha times p of zk. So p is a vector, alpha is a scalar, and if I sweep from 0 to 1, then I will get some function here. I plotted it as a convex one, but that's not necessarily true. What I know is that the Taylor series here will be something like, I mean, not something, it will be tangential to this function. That's what I definitely know. And because I know it's a descent direction, I know also that this Taylor series will point downwards. So I know that in the vicinity of my point, I will definitely go down. And what happens later, I mean, here, this could be non-convex. So it could be a nasty function somewhere else. But locally, I mean, it could also be non-convex here. It could also point down, I should say. But what I know is that if I move this tangent a bit upwards, there will be some points in this neighborhood. I mean, it could be the whole line, but it could be also some points. And that's why I draw it convex here, because I wanted to have only some points, where this is actually below the line. And these are all the points that satisfy the Amio condition. So you choose this gamma not equal to 1, because that would be too tight and would exclude, for example, our convex functions. Then there would be nothing. But you actually choose it significantly smaller than 1, between 0 and 1.5. And this ensures that you will always find a point here.
Just for clarification, could we depict the forbidden area?
Yes. I will make a better picture. So here's alpha, okay? Here's 0 and here's 1. And what I plot is v, and I maybe just say z plus alpha times p. Yeah? It holds for any p. And at this point here, so it's some function that could look like this. So I make it like this. And the only thing that I assumed is that this is pointing downwards, which I have proven here. So the direction needs to be a descent direction. So now there is the line where I would just decrease. I mean, this is the value v of z. This would be, by the way, the value v of z plus p. Is alpha equals 1, right? And now I choose some gamma. So for example, gamma a quarter I could choose. That would be this line. Maybe I do it with a color. So yeah, I think it's, everything above this line would be forbidden. So that would be the Amio condition. And so what would be allowed and what would be forbidden now? This is satisfying the Amio condition. This is also satisfying the Amio condition. And these areas here, they would be forbidden. And that would be forbidden, I think, until the end. So if you look at the intervals of possible choices, so here and here and here are the boundary points. And here you have green, here you have green, here you have red and red. So if you start with alpha equals 1 and then you contract a bit, maybe your beta would just be this value, then you would be lucky and you already accept that point and then you're done. Yeah. If your beta was something different, I mean you'd contract until this point first, for example, then you would still have to iterate once more and then this would be beta squared. Yeah. Okay. So, yeah. I don't plot the other, otherwise I confuse. This Amio condition, as I said, it will ensure that you really make progress, you go down, and it's beyond my interest here to prove that this will actually lead you towards a local minimum, but it does. Yes?
Yeah, but still, the first thing where we said that in the end on there should be a smaller than 0, right?
Which end? Okay, sorry, smaller equal than 1, you wanted to say?
Shouldn't be smaller than 0.
Smaller than 0.
Oh, sorry, now I see. Okay. That's a correction. Thank you. I thought it was like, the other thing is that it's equal to 0 at the point that starts. Yeah. But it's, but this is really an important correction. Thank you. Yeah, sorry. Oh, I think we need to stop. I thank you very much, and I look forward to seeing you on Wednesday. Thank you.